Well then, next thing on our list, things to do. Antifreeze, mostly what people are thinking of when they think of antifreeze are thinking of ethylene glycol. There are some more modern versions of antifreeze that are less toxic. Propylene glycol, amazingly enough, add one more part to the chain, changes the metabolism. At any rate, ethylene glycol, it's a dialcohol. It's got a sugary taste. It's got a structure similar to sugar, so it tastes sweet. And so people who don't know better might consume it, and if you do, then your liver will change it into glycolic acid. And it's not so much a problem with glycolic acid, except that if there's enough of it, that glycolic acid will mess up the natural buffering ability of the blood. Something that we heard a little bit about before we left for the break. Okay. So if the blood's too low pH, then there's an oxygen carrying problem, and acidosis, again, a word that we've heard before. What that acidosis does is mess with the hemoglobin equilibrium that we talked about, or mentioned at least earlier in the context of equilibrium, gets messed up, and that causes a problem. Interesting. Okay. Typical treatment is to get you drunk as you can get. Okay. So typical treatment is to consume large amounts of ethyl alcohol. What your body does is it then starts to focus on the ethyl alcohol and its metabolism, and ignores the ethylene glycol, so the body can eliminate what it's not using. So that's kind of a strange, perhaps, idea, but that's how you overcome ethylene glycol poisoning, is by consuming a large amount of ethyl alcohol. So the blood is just one set of a lot of different types of materials that are called buffers. What buffers are designed to do is to resist the change in pH. It's a solution that, with a little bit of added acid or a little bit of added base, the pH will still remain pretty close to the same. There's a limit, so we'll talk about those things. And where do you get these buffers? Buffers are a mixture of typically a weak acid, and then the salt of that weak acid. It can also be made with salt, that weak base. In practice, they tend to be weak acids. So a weak acid and its conjugate base, the salt of that same weak acid, together constitute a buffer solution. So one example, acetic acid and sodium acetate. That acetate part of it is the conjugate base of acetic acid. The sodium here is a spectator ion. The presence doesn't really make any difference whether it's sodium or potassium. Those are the typical choices simply because of the salt. Also the salts. All potassium salts are soluble. The way a buffer functions is through something called Le Chatelier's principle, which we talked about before. Thank you. So at the top is an equilibrium that we have seen before. It's the equilibrium of the weak acid. Put a weak acid in the water, it decomposes into the hydrogen ion and the conjugate base of that corresponding weak acid. And the equilibrium that we have looked at before is this equilibrium. So we talked about things like, hey, if I take 8.1 molar some weak acid solution, what would the hydronium ion concentration be? And therefore, I could determine what the pH of that solution is. Okay? The expectation there is based on the only thing I put into the water was that HA, that weak acid. At the very beginning, there was absolutely none of that conjugate base, the A minus in this case. There was none of that conjugate base present. So the only source of that conjugate base was from the acid. And those equilibrium studies that we've looked at so far with our ICE diagram, right, initial, change, equilibrium, in those we were not interested in how much A minus was produced in the first place. The conjugate base of that didn't really matter to us because we were looking at pH of these weak acid solutions. So all we need to find out is hydronium concentration. Well, what a buffer does is not simply rely on the small amount of conjugate base that's going to be formed. But what we're going to do is we're going to put in a significant amount of conjugate base. And so what we do is we have a large amount of this and a large amount of that both together in the solution at the same time. The only way you can get that is to actually put both of them in there at the same time. Just put the weak acid to get a very small amount of the conjugate base. And if we choose to just take sodium acetate and put it in the solution, we also talk about the equilibrium of that. That's a conjugate base of a weak acid, which is a significant base, which then produces a different type of equilibrium. But we investigated those equilibriums and looked at the pH of those solutions as well. Now what we want to do is look at the mixture of the two. And the mixture of the two constitutes a special substance that we call a buffer. And now the Chatelier's principle kicks in this way. By putting in a significant amount of that conjugate base, what it's going to do is push the equilibrium of the original weak acid. Which way? The Chatelier's principle. If I add something to the right-hand side, which way does the equilibrium shift? To the left. Okay. So if I add some of that, it's going to push the equilibrium this way. For our purposes, what that means is it's going to change the hydronium concentration. What it's going to do is it's going to push the hydronium concentration down. Because when you shift to the left, you must consume the materials that are on the right in order for that shift to occur. That was one of those details that I mentioned, and we haven't really focused on. That's exactly what happens with the shift at equilibrium. It will come back to equilibrium. The K value does not change. The individual quantities of each of the components can change. But it's that ratio of products to the power of their coefficients divided by reactant to the power of their coefficients. That entire ratio does not change. That's what equilibrium. But the amounts of the individual materials will change. So when I add some A minus to the right-hand side for stop equilibrium, it will push the equilibrium to the left, which for our purposes means it's going to consume hydronium. And if you consume hydronium, what happens to the pH? So if you have less hydronium, pH goes this way, up or down? Go up. So the first thing that we notice about a buffer is that the buffer itself is going to have a slightly higher pH than just a pure solution of the weak acid is going to have. And that's because we've added some of that conjugate base. And for me personally, that's how I can keep track. I've added a conjugate base that is a base. It's going to act like a base. And what bases do is they tend to raise the pH. So we've got a weak acid, we've got a conjugate base, we've got the two put together. We've got the Chatelier's principle working. The cool thing is, once I've got this thing all set up, I'll get rid of some of these extra marks. Once I've got this thing all set up, so I typically do roughly equal amounts of the conjugate base and the weak acid. Once I've got it set up, then I have this buffer, and what a buffer can do is it can control pH. It can withstand changes, something that would typically change the pH. It can moderate those changes. And again, we've used that description. It resists changes in pH. The pH does change, but it changes by a smaller amount than it otherwise would, with additional added acid or base. So, Chatelier's principle. There they are. When you add a base to this mixture, that base is going to react with the acid. Remove it, But you're going to have conjugate base in here to shift the equilibrium back to replace it. So you kind of restore the balance again. Still not quite equal amounts of the two, but still close enough because of this equilibrium. So here's the idea. I've got this equilibrium set up. My boxes are trying to show quantities. So the purple box on the left is about the same size as the, I'm going to call it yellow. It's the yellow box on the right. Because we have roughly equal amounts of those. And then the hydronium is what it is. We don't have any control over the hydronium. As soon as we get these two quantities into equilibrium, the hydronium is going to land at some level. Something we don't, at this moment, have a lot of control over. We will learn later how to control that hydronium amount. We'll do it by shifting the amounts of these two. But for right now, we've got an equilibrium, and we've got equal amounts of the weak acid and the conjugate base. And so the hydronium is what it is. And so when we step into here and we add a little bit of base to this, the base is going to react with which one of those? The acid or the conjugate base? This hydroxide is going to react with one on the left, one on the right, and the answer is? Okay. So, yeah, one on the left. That's exactly what bases are going to do. They're going to react with acid. What that's going to do is reduce the amount of acid, and in the process, it's going to form some anion, the same conjugate base that's already in the system. That conjugate base, of course, is going to increase the amount of conjugate base that's on the other side. So once you add a little bit of base to this buffer, you will have a little bit less of the weak acid, and you'll have a little bit more of this corresponding conjugate base. Of course, if that happens, then this hydronium is going to change. But it's going to change by a small amount, and that's really the key to the buffer. That hydronium is going to change by a small amount. Same equilibrium, only this time, if we go in the other direction, if we add some acid to that equilibrium, then when you add acid to this equilibrium, it's going to shift to the right. That shift to the right is going to tend to increase the hydronium, but basically it will help reduce the amount of that shift. So here's the same original buffer, not the one we just added hydroxide to, but back to an original example where we have equal amounts of weak acid and constant base. We're going to add acid to this. This time, of course, the acid is going to react with the conjugate base from the buffer, changing some part of that conjugate base into the original weak acid, which, of course, in the equilibrium is really part of that component right there, and it will increase. So it will increase the amount. Give you the increased amount of the weak acid, and the decreased amount of the conjugate base, which of course is going to change the hydronium, but not by as much as you might think. This buffer is one example of something called a common ion effect. It's one of the things that you talk about when you talk about equilibrium in the general chemistry course. A common ion effect. What it means is we have an equilibrium, but what we also have is an ion that's already a part of the equilibrium that we have modified, that we have artificially adjusted, that is also present in the solution, however you want to think of that. Right? So rather than just simply the weak acid changing into these guys, so that's the equilibrium that we talked about. The common ion effect says, I'm going to add in something else. And in this context of a buffer system, that something else is that ion right there. It's the conjugate. what I'm going to do is I'm going to put into the solution an ion that's a part of some other equilibrium. But it's the exact same ion. So that's why it's a common ion. And the effect of that is to change concentrations. So it's going to impact the equilibrium. We'll talk more about common ion effects later on when we get to solubility. We'll learn there that there's other ions that have in common, and those ions will also affect the equilibrium for those situations. So let's see, on the left here is a standard acetic acid solution at 2.1 molar. If you get some high precision, put a pH meter in there rather than just rely on the paper with certain colors, where you would do it today. Then you get a little bit more precise here. So pH 2.9 is acetic, 0.1 molar acetic acid solution. We know how to calculate that, by the way. We know the K for acetic acid. We can put that into an ice diagram. We can find x squared, solve the root of that. We can expect that x will be small for the change. Do some simplification of our math. And determine the value for x. X being the concentration of hydronium. And then take a log of that so we have pH. We should find the pH of acetic acid. 0.1. And then we also, by the way, learned how to determine the pH of a sodium acetate solution. That was that pseudo-nightmare stuff where you had to figure out, okay, sodium ion. It is the constant acid of a strong base, so it's not very acidic. So sodium ions in solution are not acidic, so they are what we call pH neutral. That means they don't impact the pH. Anything in group 1 and group 2, those are pH neutral cations. It's the transition metal ions, especially the ones that have a +2 or +3 charge. Things like aluminum is a 2+ automatic. Things like iron 3, things like chromium 3. Those kinds of ions are acidic ions. They're going to push the pH to the low side. And then you've got the acetate, the other part of the salt. You've got sodium acetate, you've got to consider the sodium ion, you've got to consider the acetate ion. These are the things that we talked about that the acetate is the conjugate base of a weak acid. The conjugate base of a weak acid, then it will have significant, I'll try to use that word again, it will have significant basic properties. I'm not saying it's a strong base. I was using that kind of word, but I'm avoiding it. So, is it a weak base? Is it a strong base? Is it okay? I don't want to do that. It has significant base properties. That's how I would say it. So, the acetate has significant base properties. The sodium ion has no impact. So, I would expect the pH of a sodium acetate solution to be on the basic side. Definitely higher than pH 7. Those are the same kinds of skills that you walk through, and I expect you guys to accomplish as well. Now, the fact that it's exactly 8.9, that's a whole different issue. All I can say on the basis of sodium and acetate is that the pH is going to be higher than 7 because of those two ions and the way they operate. However, if I know the Ka or acetic acid, I can use it to determine the Kb for the acetate ion. And knowing the Kb is an acetate ion, and knowing the concentration of that sodium acetate salt, I can use an equilibrium in an ice diagram, initial change equilibrium, and I can calculate the pH of that 0.1 molar sodium acetate solution is going to be 8.9. So the first calculation on the left of acetic acid being 2.9, you guys can do that. All you need to have is the Ka value and an ice diagram, and you can work it out. Sodium acetate, 0.1 molar, yep, sure it is, 0.1 molar. You guys can calculate that as well, because you know that Ka and Kb are related. Right? Ka times Kb is Ka minus 14, because that is for water. So if I know the Ka for the acid, I know the Kb for the conjugate base. Always the case. If I know the Kb for a base, I know the Ka for the conjugate acid. Always the case. So we can do those two methods. What we're going to add in this chapter is the one on the right-hand side. How to calculate the pH when you have a mixture of those two materials. And you may think it should simply be halfway between these two. Halfway between 3 and 9, I'll round it to make my math easier. Halfway between 3 and 9 is halfway between 3 and 9 is 6. So if I have equal amounts, 0.1 molar of acetic acid, 0.1 molar of sodium acetate, you may think the pH of that mixture should be 6, but as you can see, it's not. It's closer to 5, actually a little bit less than 5. It's closer to 4.5, rather than halfway between the two. First thing you should realize, it's not halfway between the two. But there is a relatively simple formula that involves that. It's called the Henderson-Hassel bond. So you were using it the other day in lab when you filled out that table and you said 1 out of 4 drops, 2 out of 3 drops, 3 out of 2, 4 out of 1 in that table, and then you plug it into the Henderson-Hassel bond, and we'll get to that soon. Meanwhile, let me come back to where we're at today. Common ion effect. pH of the acetic acid is 2.9. The pH of the sodium acetate is 8.9. When you put equal amounts of the two together, you get a pH that is higher than the acid. If you reduce the amount of hydronium that's at equilibrium, that is part of the common ion effect. The common ion effect is going to reduce the amount of hydronium produced from that acetic acid. So you get a pH in this case of 4.7, and again, before we're finished with this chapter, you guys will learn how to determine and calculate that pH of 4.7. Actually, like I said, you worked with this idea, you already did a similar calculation in lab. So let's consider how to get those numbers. If we didn't have a pH meter and want to know what the theoretical values are, we can figure out what they are. So here we go. What is the pH of a buffer that is 0.1 molar in acetic acid and 0.1 molar in sodium acetate? Now, previous slide, the right-hand mixture, that's exactly what that is, all right? So we actually already know we're expecting a pH value of 4.7. That's what I see from here. But let's do a calculation and let's figure this out for ourselves. First thing we have to do is figure out what equilibrium we need to look at. And what I need to do is figure out an equilibrium that will satisfy both, or that contains, if you will, both of these two. The simplest choice for that is the equilibrium of the weak acid itself, which we've seen before. So we take acetic acid and water on one side, in equilibrium with the conjugate base of the acetic acid, which is the acetate ion, and the hydronium on the right. Cool. The nice thing about this equilibrium is, if I'm looking for pH, I need the concentration of what in this equilibrium? So that's the nice equilibrium here. This one's going to give me a value for pH pretty quickly and directly. And the nice thing about that equilibrium is it contains both of these two parts of the buffer. It's got acetic acid in it, it has the acetate. It does not have the sodium ion in it. But wait, sodium ions, there's a spectator here. Sodium ion is one of those ions that's not going to influence pH anyway. So it doesn't matter to me if this is a sodium acid. The sodium is an aluminum particle. You have to have the sodium that will have sodium acetate acetate is an anion, can't exist by itself. You cannot go to the shelf and get a bottle of acetate without any anion. Non-compounds don't work like that. You cannot get a electromagnetic ion. It's not possible. At least not in solution. You can get them in the gas phase, but that's really weird and strange and nothing that we will work with. So there we go. Oh, next thing we're going to do is make an ice diagram. You bet. And what you should notice is this ice diagram has a couple of values already put into it. And hopefully you can see exactly where those two values come from. So just like we've always done in the previous chapter, we've got our 0.1 molar acetic acid. Oh, but wait. Previously, if this was just acetic acid, then our acetate would have been a 0 as well as our hydronium would have been 0, right? Well, this is a common ion effect. So we have another ion present, and so we've got to start our initial with that idea. So we start the whole thing with 0.1 molar acetic acid, 0.1 molar acetate. We still got 0 on the hydronium, and you see that approximately 0. What's the actual value? 10 to the minus what? 7. 10 to the minus 7. That's pretty small, especially compared to 0.1 molar. So that's why we're saying approximately 0. As far as we're concerned, it's 0. Change. Let's see. What am I going to use for change? Yeah. Change in is what? Negative here. Okay. X. Okay. A minus. Okay. If the HA is negative X, this one has to be plus X. And the hydronium has to be plus X. Okay. How do I know whether the HA is going to decrease or increase? How do I know? You said minus X. Why don't you choose minus X? How do you know if it's going to go deeper down? Because that's what minus means. You can change this number down. Okay. So how do you know it's going to go up or go down? How do you know that the A minus, the conjugate anion, how do you know that that one's not going to actually be going to decrease? To some degree, we actually are. Okay. Now, if I really want to know, there's a mathematical way to do that. And it involves the letter of the alphabet, Q. Okay. If I really want to know, I would do a Q calculation. Me personally, I don't. That's not the right phrase. It doesn't matter. Okay? It doesn't matter. If I've chosen wrong, when I get to the bottom, I'm going to get a negative answer, and it's going to tell me I've chosen wrong. Which simply means that I picked the wrong direction at the beginning. The value numerically will still be the correct value. I just need to change the sign and get on down the road. Which is why personally I never do a Q calculation. I don't. Plus I've got one more clue here to help me. If the hydronium truly starts at 0, there's only one way it can go, right? It can only go up. So if it truly starts at 0, it cannot go down. So it has to be a positive X, and then that forces everything else to be in a particular direction. So if you want to be sure, do a Q calculation. You're welcome to it. Personally, I do not, because I know that hydronium is going to have to be more than 0. It's going to hit the equilibrium. So I know that's got to be plus X. All right, so that makes my equilibrium, that value is X. This value is 0.100 plus X. This one is 0.100 minus X. You guys probably figure fill in those values yourself. I've been doing this for a while, so hopefully this is like second nature to you. And you know exactly what to do from here. First thing I'm going to do before I start doing any more math is to do what? Okay, I need to know the K value. That's true. I'm going to do that approximation, which says 0.100 minus x is still pretty much 0.100. 0.100 plus x is also still pretty much 0.100. But yes, I need to know the K value. And actually in your book, example 16.1, which is on page something. If not, if it doesn't tell you right there in the sample, there's a chart in the previous chapter. There's a chart in the back of the book. Does it give you close by the K value? 1.8 10 to the negative 5. Okay. So I know that value. So what I need to do is 1.8 times 10 to the minus 5 has to be equal to products on top, 0.100 times x divided by reactants on the bottom, 0.100, and water is a liquid, so it's not included as probably right? We've never been including the water part. Oh my, hey, this math's looking pretty simple to me. So let's see, 0.100x on top, 0.100 on bottom. I'm going to cancel those two out, and so right quick like the value for x is 1.8 times 10 to the minus 5. So the pH is simply the negative log of x, which is the negative log of 1.8 times 10 to the minus 5, which is 4.74. That's 3 significant figures. That's 3 significant figures up. That's under 2. So 4.74 is my pH. Yeah, the nice thing about acids and bases are the coefficients of that. And yes, whenever those two amounts are equal, as long as the x is small, approximation works, right? We didn't check that. Is it okay? Is x small is less than 5%? You guys checked it too. What? You just assumed it is? Oh my goodness. So, oh, okay, awesome. Of course, my rule was this initial amount is 10 to the minus 1. The K value is 10 to the minus 5. That's a 10 to the 4th difference. That's a 10,000-fold difference. That should be enough to make the x a small approximation of value. But of course, if you want to check it, you take 1.8 times 10 to the minus 5. That was 2, yeah. Then you divide it by 0.1. See what that's like. Plus it says it in the book, so it must be. Must be right. Yeah. Now what was I expecting the value to be? 4.7 according to my pH. So yeah, right on the money. 4.74 projection. So let's see, what we did. This is what we did. We put 0.1 in there, and I said that that's going to decrease because really, for me, the hydronium is going to increase. So that causes the signs to be what they are. So at equilibrium, we've got 0.100 minus x, 0.100 plus x, and x. As long as I plug this in to K, and as long as x is small, man, it makes my math a whole lot simpler. You bet. Otherwise, I'm in a quadratic. That's what I'm going to end up with here, quadratic. So, if the x is small, then that's nice, some math right there, that those two cancel out, and sure enough, the K value is the hydronium ion concentration under this special circumstance. And yes, Willa is correct, that as long as you have equal concentrations of your weak acid and its conjugate, you can see that the math is always in a falling way. So if I chose it 0.5 molar and 0.5 molar, you can see that they're going to change. What we have found is a special situation, special circumstance. And by the way, I told you previously that that 4.7 we don't have a lot of control over. Because where did that B 4.7 come from? It's the negative log of 1. Okay, technically it's the negative log of H3O, but what is the concentration of the H3O? It's the Ka, that part. So that H3O's concentration, that hydronium concentration, under this circumstance, is just simply the Ka of that weak acid. So here's the first thing I want to plant in the back of your mind is the pH of that buffer is going to be somehow related to the Ka of the weak acid. That's what I mean by I don't have control. I don't have control of what that specific pH is going to be. No matter whether I use 0.5 molar of each, 0.2 molar, 0.1 molar, it will not change the pH by my calculation, right? So the only thing that's controlling that is Ka. So if I want a different pH for my buffer, I need to choose a different pH. Which is why the hydrogen carbonate and carbonic acid equilibrium buffer, the pH of the blood is 7 point. We have to between 7.35 and 7.45. So that pH 7.4 is controlled by the carbonic acid. That's the Ka of the carbonic acid. It's related to that. Okay, let me finish this up. So, Ka is 1.8 times 10 to the minus 5. That's what the value of the hydronium concentration is, yes. And so the negative log of that is what the pH is. Definitely way under 5%. Super technical. Don't really care what acidic is. Don't really care what acetate concentration is. Boom, that's the hydronium. That's what I want. And so the negative log of that gives me pH. 4.7. The negative log of the Ka is going to determine the pH. Questions, comments so far? What we've done is with the common ion effect, we've added one change to our ice diagram. Instead of just having initial concentration of a weak acid, or just having initial concentration of a conjugate base, now we have initial concentration of both. So there are two initial concentrations. That of the weak acid as well as that of its conjugate base. So we've added to our just one more thing. That's all we've done. Everything we've been talking about before. So pH is 4.74. If you want to go back and calculate the equilibrium value for everybody, then you can plug it in and you can check it just to make sure. Okay. Again, you should do this. But I'll confess that personally I don't. I have enough experience that I know that the pH has to be close to the negative log of the Ka for a buffer system. So knowing the negative log of the Ka, oh wait a minute, negative log of the Ka. Okay, that sounds familiar. Oh, right. Wait a minute. Negative log of anything. Right? Negative log of anything. So I know that the pH of this buffer has to be somewhere close to the pKa for that to be correct. So that's my reminder. That's my personal check. Knowing what the pKa of acetic acid is my check. But if you want to go calculate and you want to put them all in and you want to calculate and see the pKa that comes back, that's perfectly fine. Okay? Whatever works for you. All right. Your turn. So take a few minutes, run this calculation, see what you get, and then we'll take a break.